All right, so AMP kinase can prevent TSC2 movement away from Reb, keep Reb inactive, and prevent the activation of mTOR. So in theory, then, if you were to activate AMP kinase in skeletal muscle and then do resistance exercise, or even do resistance exercise and then activate AMP kinase, you should be able to block the activation of mTOR. And the first paper that looked at this was by Thompson and Gordon, and basically what they did is they did resistance exercise. They had injected the animal either with saline, salt water, or ICAR. And ICAR is a poison that activates AMP kinase, because if it's a poison, you're going to get metabolic stress, because most poisons are metabolic poisons. They do something wrong to the mitochondria, so you can't produce energy. And so what they then did is they then did resistance exercise. They looked 40 minutes after resistance exercise, and this is S6 kinase phosphorylation at 389. And what you can see is that in the saline group, you had this really nice, robust increase in S6 kinase phosphorylation, and in the ICAR stimulated group, you see almost no activation of mTOR. So completely consistent with this idea that if you activate if you activate AMP kinase, you're going to block mTOR activity. All right. Then you follow that up with this beautiful paper from Jacques Mournier's group in France, where they took the AMP kinase alpha-1 knockout mice. They did overload, and what they looked at is they looked to see how much the muscle grew following overload. And no matter whether you looked at 7 days or 21 days, the AMP kinase knockout muscle had a greater increase in muscle mass than the wild type animals. And what that suggests is that AMP kinase is providing a break. And specifically in this case, the alpha-1 AMP kinase is slowing the increase in muscle mass that's caused by overload, which we already know is driven by mTOR complex 1. All right, so this looks all perfect. So obviously when you exercise, you're going to activate AMP kinase, and that's going to block your mTOR activation. Problem. Will Apro, who had come to the laboratory from Sweden and done some work with us and then went back home, what he did is he did a simple experiment where he did resistance exercise, or he did endurance exercise followed by resistance exercise, where he made sure that the endurance exercise activated AMP kinase. And so when the AMP kinase activity high, he did resistance exercise. The resistance exercise was done before the endurance exercise. You can see that here, rest plus endurance exercise, rest plus, and then, resistance exercise. And what you can see is 90 minutes or 180 minutes after resistance exercise, or after the exercise bouts, you can see that S6 kinase activity is going up in these people. But when you do the exercise together with the endurance, so lifting weights with the endurance exercise, you can see that technically there's no statistical difference between them. If you squint, you can see that the resistance exercise response is a little bit blunted in the endurance exercise. But it doesn't block it completely the way it did in the animals when you injected them with ICAR. And so now there's this question, this doesn't work. Everybody is now all upset that, this was just, this molecular stuff is ridiculous and it doesn't really work that way. But you should have already seen something. So which flavor of AMP kinase when you knocked it out, caused an increase in muscle mass? The alpha-1. Which flavor of AMP kinase is activated by endurance exercise? The alpha-2. So already we're seeing that maybe an alpha-1 AMP kinase only goes up a little shade with endurance exercise. The kind of shade that might get you something like this. All right, so then this is a bit of a problem, because the one that's blocking growth is alpha-1. The one that's activated by endurance exercise is alpha-2. So how could this happen? And if you look actually in AMP kinase knockout cells, complete knockout cells, you still see when you take out the glucose, even though here's the control, so you can see these are wild type animals or wild type cells, they have alpha-1 and alpha-2 AMP kinase. You can see that when you take out glucose, you get a decrease in mTOR activity. In the alpha-1, alpha-2 knockouts, now you still see a decrease in glucose. All right, so what's going on here? what's happening? Why are we seeing that glucose still has an effect if it's not just being driven by AMP kinase, and specifically by this alpha-1 AMP kinase? All right, so now let's try and figure this out. So what this group did, and this is a really interesting paper, and what they did is they pulled down the regulator, and they wanted to see, does AMP kinase interact with the regulator? In glucose starvation here, you can see that AMP kinase interacts with the regulator, and it goes up from this AMP kinase that is there with glucose when the glucose is normal. And then they knock out a protein called axin. And axin is this interesting protein that is just a chaperone protein. It's a lot like IRS1. And so what it's doing is it's carrying AMP kinase. So if you knock out axin and then you do the glucose starvation, there's no appearance of AMP kinase at the regulator. All right. You can see that in the axin positive cells, when you do glucose starvation, there's no raptor there. You decrease the amount of raptor there. You can do the same thing here with the axin. You do still see a decrease in raptor, but it's not complete. So what seems to be happening, and the other thing is when you have the knockout, when you have the axin positive cells, mTOR is not at the regulator. But when you have the axin knockouts, now mTOR is at the regulator. All right, so now it seems like something interesting is happening. That something is moving AMP kinase to the regulator, and it's preventing the movement of raptor and mTOR to the regulator. And that something seems to be this protein axin. And so what axin seems to do is it seems to act as a scaffold. And what it does is it comes in, and what it can do, what apparently it does, is it takes the lysosome, and what we think is happening is that alpha-1 AMP kinase is either together on the lysosome or it's together with axin itself. When there is a signal of metabolic stress, of energy deficit, axin now moves to the regulator, and it binds to the regulator. And when it binds to the regulator, now look what it's done is it's brought the activator of AMP kinase to AMP kinase. And now from here, AMP kinase can directly phosphorylate TSC2, and it can do other things within the cell that we'll talk about later. The other thing that happens is axin, by binding to the regulator, is interrupting leucine signals. So it's interrupting the sestrine gator2, gator1 signal. And so now what we've got is we've got a break. So now what you're doing is you're lifting weights. That's great. And so the lifting weights is pressing on the accelerator. You're going to go faster. You're going to grow. But when you're doing the endurance exercise, it's like lifting the weights, accelerator, and doing the brake. And so now you've got the brake on while you're trying to accelerate. And so the endurance exercise is working as a brake. And it's really this axin molecule that's coming in and it's interacting with the regulator and it's preventing its activation by this leucine stimulated pathway. Okay? And it's increasing AMP kinase activity local to the regulator, or to the regulator. So it's close to TSC2 and it's close to other things that are really going to be important for shutting this system down. All right, but that should get your brain going as to, how can we get around this? How can we override this? And we'll talk about that in a second.